Hello, everybody in bioinstrumentation. This is Dr. Keith Schubert. So, I want to give a little bit of a MatLab sampling of how we can use independent component analysis. So, to do this, I first needed to make some data. So, you can see here the first 24 lines of data, or 24 lines of the code here, is where I generate the data that we'll be trying to analyze. The reason why we make up data for these type of areas is so that we kind of know what the answer in advance is, and so we can see if it does what we anticipate it to be able to do, and we can then test it on these kind of known cases, and it gives us confidence for the cases where we don't know what it is. It also allows us to see if we can generate certain types of data to give us insight into um, what different patterns in the data might mean. So in this case, I'm going to generate 2,000 points. This L feature is going to be the length of the data spread versus its width. So it's going to be um, kind of an ellipsoid that's 20 times longer than it is wide. We're going to generate two of them. So we're going to make XY pairs, Gaussian random noise. You can see in the X direction, I'm making it 20 times longer. I then stack the X and the Y points together. So that makes this, the P1 is just a bunch of points. And then theta 1 is a rotation angle. So in this case, pi over 12. You can see I've got a rotation matrix here, the cosines, sine and minus sine on the off diagonal. So when I multiply that rotation matrix times the points, I get the rotated points. So that's going to basically take that point cloud and put it on the angle of pi over 12, which is about 15. Well, it's 15 degrees exactly. So the second group, I'm putting, deliberately I picked an angle that's close. You can see I've made another section of points basically the exact same way. I've got a different rotation angle. This one pi over 7. So it's just designed to be nearby, but sufficiently different so you can kind of recognize them. And so I rotate that one, and then I just append them. So I get a total of 4,000 points. That makes up my measured data of two overlapping point clouds, one at angle pi over 7 and the other at pi over 12. Then I'm going to do FastICA on that measured data. For quick use here, I just kind of put some of the options we're going to take a look at. By default, it's going to use a deflation method, and it uses a power in x cubed as the nonlinearity function. And it's then going to return the data that has been kind of cleaned and rotated. It'll have the directions and then the mixing or weight matrix. So that's kind of what it's trying to figure out. Then we'll have a figure, and it'll basically plot what the data should look like when it's clean, and we'll plot the measured data, and then on top of that, that's what the hold on is for, I'll basically plot the axes from the A matrix. So this will say what direction it found the data to lie in, the principal directions, and then last it'll plot the data itself. So I'm going to run this script, and what you'll notice, I get undefined function. Now I did this deliberately. I actually had this all nice and working, and then I exited out, because if you ever try to run code like this, I'm using FastICA, which is not built into MATLAB. So when you run these type of codes, you're not going to immediately have it within your path. So in this case, FastICA is something you can download, and in order to add it in, you have to actually, on a PC it would be right click, on a Mac it's control click. You pull up the extra menu and you have to tell it to add to the path. And I'm going to add the folder and all of its subfolders. Now that that has been added into the path, if I were to run this same code again, it will run perfectly. So I just did that. If you ever run into those weird error messages like that, that it says it can't find things, just make sure you add it to your path. It's a common problem I've seen a lot of people have. And you probably all saw this at one point in your past where you have to add that in. But I've noted after people haven't used MATLAB in a while, it's an easy one to forget. So that's just my reminder. So you can see the point clouds now, and you can see the two different angles. You've got the pi over 12 and the pi over 7. Now, if I were to do PCA, by the way, it would go right between the two, and then it would find the off direction because it's going to find the point of maximum variance, i.e., what direction can it get the longest run? And the longest run it can get is going one side to the other right through the middle because they're two symmetric clouds. Um, so that's going to give you an off direction. Anyway, if we were to zoom in here, you could actually see there's tons and tons of data points making up these clouds. So that's the first one. That's just what the data originally looks like. Now you can see here when I plot this in, you can see the red lines. It actually found the main axes lines that both of these point clouds are on. So um, that's what you can see for both of these. So ICA actually did find the correct directions for both of them. And so that was contained within our A matrix. It told us the direction that these lie on. And then finally, it will now give us the corrected data where these two axes will be made the principal orthogonal axes of our data cloud. And so you can now see that's now orthogonalized that data cloud. So you can see them broken up kind of into their independent directions. So you can see the two clouds broken out. That's basically the way that this works. Now, it does a good job here because this is a fairly straightforward problem to be able to get in. Now, if we want to do some things deflate, right, you'll see this. There's some other ICA methods that are out there. What deflate means is it will do one at a time. It'll find the easiest one that it can get, and it will try to remove that from the system and then try to find the next easiest. The symmetric, which is sometimes called parallel, is another approach to solving the problem, and it tries to find them all simultaneously. So, there's cases where each one works better. Deflation tends to be a little bit less computationally expensive because rather than solving a whole bunch of big problems at the same time, you solve one big problem, reduce it, solve another problem, reduce it. So it's a little bit easier. It's kind of like nibbling the pieces out. That can, however, cause some error buildup. So if it's a very sensitive system, you might actually have to do the symmetric one. In this case, you've got different nonlinearity functions. So the defaults work well on this because it's a straightforward problem. I think it's a good imaging problem, but it's a pretty straightforward one that's on. But you can also use tanh is a very common one. Skew is used if you have a reason to believe that you have a skewed piece of data. So if you think the frequency domain, if you got a lopsided tail, skew works. So skew is one of those ones that it either does a great job or it does a horrible job. So if you really have skewed data, it does a great job. If you do not have skewed data, it will look absolutely horrible as a result. So if you try skew and it ends up horrible, don't do it. Gauss does not mean that it's saying that it's necessarily Gaussian data, but it is saying that you are using the Gaussian function, the e to the minus x squared over 2. Sometimes they have an alpha parameter in front of it. But basically the minus x squared, e to the minus x squared is the basic Gaussian function. And that actually is a very common nonlinearity, or at least approximates a lot of stuff. So it's actually using it more for its nonlinear form, actually, than it's as a particular probabilistic distribution. Anyway, so we can, if we want to, this one, like I said, deflate is the standard. We can actually do the same thing symmetrically. So all we do is I just copy that in and paste it, and I can run. Right? And you can see it's trying to solve this. So it actually kind of, while trying to solve it simultaneously, did a job much more similar to what we would get with a PCA. because it didn't find whichever one was bigger first and then try to remove it. So um, in this case, symmetric did not do as good of a job for us on figuring it out. So we get this kind of rotated because it split between the two. Um, Now, since this is a random algorithm, I'm not guaranteed to get the same thing every time. I might. Yeah, you can see. So I read again, since it is a probabilistic, it takes a random guess. If it guesses badly, it will get something screwbally. But in this case, I ran it again, same exact thing, and this time it had a better guess, and it actually found both of the directions simultaneously. And you can see it found both of them, and then you can see it runs off. So this is another one of those areas. It's often helpful to run ICA a few different times, um, just because it gets a wrong answer the first time. Remember, these are probabilistic iterative algorithms. So if I were to run this multiple times, you'll see, right? It tells you there is kind of a little bit of a difficult area for it to resolve between these two. And so there's some stable points in between that it's trying to solve off. So it's again kind of picked on that main axis, and it was probably starting to pull down. This is doing symmetric. So it would have started right down the center and right off the side. That would be where it would get its initial um, estimate out of PCA, and it would pick some random start around there, and it was just too slow. You can see it's kind of pulling up from the center line. It's just moving slowly, and this one's pulling from the side too slowly down. So um, in this case, it didn't get all the way, and you can see it just starting to rotate. Another thing I could do is increase the number of iterations. You can see it tells us in the command window. Um, After 1,000 steps, it says no convergence. So it knew it was moving towards it, but it hadn't reached it yet, which means it's very slow in that convergence area. So I might want to change my function to help it out. It sometimes gets it, it sometimes doesn't. Um, so we can say, hey, what if we tried skew? Now, skew should be pretty bad for this because this is not a skewed function. But sometimes it will help us. And in this case, it actually did a good job, which I'm a little bit surprised on. It's still not perfect. You can see this one's a little bit too far out, both of them. It should have been a little bit down, but it did actually get us into the general area. Um, you can see on here that that's not perfectly lined up, but it definitely was doing better than um, the X cubed is doing, which also has a little bit of a skew to it. Let's try instead 10H is a one that works quite well usually for an awful lot of them. So you see our data plot. You can see again it's going. It hasn't fully converged yet on this. Um, so when doing them symmetrically, it is not as nice because again it's got to get two large problems to converge. And this is often a challenging one, which is why deflation is big. So for smaller problems that are sensitive, symmetric helps, but it can be a little bit of a challenge otherwise. Let's try Gaussian on this as our nonlinearity. And we'll see if it, so that one got us dead straight on. Now these are Gaussian ellipses because it came from a Gaussian distribution. That's not too surprising that it's able to solve on there. And we can see it's pretty well lined up for each of these. We'll see if this works a couple times. A good way to tell, since it is random each time where it starts off, yeah, see it's pegging it each time. So we've actually found a good function here for the nonlinearity to be able to get them. We can see it's consistently giving us the right answer. Yeah, 3 times in a row. The other ones, it was pretty random. We'll just, so you can see on the other ones, sometimes they do well, sometimes they wouldn't. You can notice it will pick different directions on them. Um, either the positive or the negative between each, but um, it's hitting it every time. So we can see Gauss did turn out to be a very good function here because it gives us that kind of elliptical function that we wanted to be able to properly fit our data. So that gives you an example on a point cloud. This one is actually on extrapolating waves out. So in this case, I picked a time period that just goes up to from 1 at steps, fractions of pi, up to 8 pi, and I'm using a sine wave and a sawtooth wave, right? And they have different frequencies, so they don't line up nicely. And then I just have rand, so rand by default is going to give you a uniform variable. I have a mixing matrix for these 3 different waves, S1, S2, and the random noise. I then take all 3 of those signals, multiply it by the mixing matrix, and that gives the measured data. And then we'll pass it into FastICA, and we'll plot the measured data, what the extracted signals are, and then what the real signals are. So we'll run this, and again, this is using the default parameters. Right, now, if you look at this, this is not a particularly huge sample. You can see on the triangular wave, it still has a little bit of that sine kind of stuck in there. You can see some of it's not, the sine has an up and down to it, a very sharp discontinuity. The noise has a little bit of a drifting baseline. This was the original data. You can kind of see it has been cleaning it up, but it didn't really get it perfect. You can see the height variations do carry through, and that discontinuity at that point still appears. The wave on the triangle is still there to some lesser extent. So, I mean, it does a reasonable job, but it's not great. Let's try symmetric on this. Since it's a smaller problem and it's a little bit more sensitive on it, theoretically, we should get a pretty good job on running this by just symmetrically trying to solve for things without even changing our nonlinearity. And indeed it did. So in this case, since it is a smaller one, the symmetric solves for both in parallel, so it can kind of feed the answer back in. We find it does give us this. Again, though, it's just a minus sign difference between these two. So we don't care about minus signs or scaling differences. We just care about the shape. So the basic shape of this is rock solid on here. A little bit of noise in there, not a bad job. You can see that bit of a discontinuity still does exist. There's a little bit of a wobble here too, but it's significantly less than it was before. There's still a little bit of difference in the amplitudes, but again, it's flattening out. If I gave it more time, probably do even better. Now, we might be able to get even more by trying to find a better nonlinearity function, but by changing the approach, we can see on this one, it was actually able to bring it out. So symmetric is good in certain cases. And this is it. There's no one of these that is right all the time. Should not make this full size. Thank you. Let's try in here. I'll show you a case where skew. In theory, on this one, skew should do pretty badly. So, but we'll try it. It's always a good one to check out. Yeah, and you can see it does. Fine. I mean, a pretty horrible job. That's almost exactly here. It's kind of pulling the noise down a little bit. The sine, it did a horrible job. These are nowhere near skewed functions, so skew does a bad job on it. All right. So instead of skew, let's try, like we said, tan H is another very common nonlinearity that is used. And it did a pretty good job also in here. I don't think it necessarily is that big of a difference. It might be a little bit flatter, a little bit better noise rejection. We still do have a little bit those wobbles in those areas, and we see a little bit of the height variation. Um, you will notice the noise bigger on the peaks because the slope is slower. It's hard to notice noise when it's coming up on a very strong angle, because the noise is not going to have a big effect versus the slope. So it just tends to, um, on very strong angled ones, noise is not as influential. You can see that same thing going on here. Right? The noise looks bigger here. It's actually not, um, but it just has less of effect on the appearance and also on the zeros in it. So noise does not affect the angled sides as strongly. Let's take a look at Gaussian. So these are the ones that FastICA gives you. You could, in theory, add in your own if you wanted, or there's other ones that pick different. Um, this one seems to have done a fairly decent job also, but so it's done a better job rejecting the noise. I think the tops you see are a lot smoother. There still is a little distortion here and there, um, a little bit of a height variation, but it did a really good job of pulling the noise out. So um, I think that one actually kind of won it for the day for this one, but it's a pretty minor difference on most of these. Um, what we did see was on the first one, it was skew wasn't too bad, and on the second one, skew was horrible. So, like I said, they often will have ones that are better for them and worse for them. If there was one that was best all the time, everybody would just use that. So, anyway, um, this just gives you an idea of what you can do, how to kind of play with the parameters. And like I said, running things multiple times, since it is a somewhat random algorithm, and we see here that it didn't do as good of a job on the noise in this particular case. You can see it didn't extract it out as well. Um, it did every bit as well on this, but here there's a lot of noise. Of course, you don't see a lot of noise on the steepest slope, but you do see a lot of noise in here. So if we were to kind of zoom in, you can see a lot of noise still carried in that it still had to be able to remove. So number of iterations, that's another thing you can select when you're choosing your parameters. So you'll see here that um, so it thinks it got to an area, right? So you can see it's converging fairly quickly. It checks to see basically when this gets small enough, you can adjust that down. I forget the default. It might be like 0.01 or something, or 0.02, 0.002 or something. Usually they pick a small number, but not horrendously small. Um, so this converged fairly quickly. Um, and actually it says it goes to 4 steps. So the fourth step might have got down to 0.001. Maybe that was the break off. Anyway, you can change that value as a default. How small does that change have to get? So this is showing an error reduction. Remember, it's a step, and it's saying, oh, how much did I improve? When that improvement gets better, right, as the improvements get smaller and smaller, it assumes it's getting close to the answer. That may or may not be true. Sometimes you get to an area where it's really, really slow going and it takes a while. So you have to adjust that. You can also adjust the maximum number of steps. It's another one of the parameters, so you can look them up. So if you see something that's not letting you go far enough, adjust those. What's that? The minimum value for it. It's usually classified as epsilon, smallest step, and then the number of iterations. Anyway, this gives you a understanding how you can kind of adjust some of these parameters. This will be used by default on the system we'll take a look at on Tuesday. I just wanted to kind of let you see on a low level how we can adjust these. Sometimes rerunning it, if you get a bad result or something, not a bad idea to rerun it anyway, because whenever you're using an algorithm that's probabilistic, um, it's worth checking to see if running the same data a couple different ways adjusting some of the parameters might get you a better value out of it. All right, hope this helps, and I will see you all on Tuesday. Bye.